Hi folks, this is another video for pre-calculus work. In today's video we're going to look at some domains of composite functions, and we're going to start with this one here where the f of g of x and g of f of x functions, which are the composites, we're just going to look at the domains of those two. And one of these will probably be a little bit easier computation than the other. So what I'm going to do is, just for fun here, I'm going to go ahead and start with the easier of the two. It's going to be this one right here, g of f of x. So the first thing we're going to do is set up what I call our little buckets. I do this for each of my domains, and I'm not going to be calculating the actual composite function. I'm simply going to be using these buckets to help me illustrate what's going on with the domain and what's happening with this composite function to begin with. So as we saw in class, the f of x function is the first function that we're going to be operating on. So I tend to put an arrow this way and put f at the top of that arrow. And then the second function, after f has been executed, then we're going to go ahead into g. So this first bucket is imagining this is all the real numbers in the world, and they go into f. So let's begin with that f function. In this case, we're looking to see that in this function, is there any restriction on x? So we'll start with our domain at the bottom here. X such that. All right. And we see, because it's a radical, that x, numbers coming out of the real bucket, have to be greater than or equal to, it looks like the number 1, because x minus 1 would be 0, and we don't want any negative numbers under this radical. So that's the first thing. And that's going to go right down into our domain. We're going to put that in there right away, greater than or equal to 1. And that might be further changed as we move along. Now we know this first bucket over here is going to be the answers for f of x. And over at the g function, that's this guy right here, we see that x cannot equal 3, but we don't write it that way. We write it that f of x cannot equal the number 3. The answers coming out of f of x cannot equal 3 because this is a composite function. And let me just write it here, g of f of x. So as you can see, it's the f of x values that can't be equal to 3. And the funny thing about it is we simply set the f of x function, x minus 1, under a radical here, equal to that crazy number 3. And if we square both sides, x minus 1 is equal to 9, and so x is equal to 10. And we call this the culprit, or the rascal. The rascal is the number that started way over here in the real bucket and ended up answering as a 3. So if you put in the number 10, this number 10 right over here, and you plug it into, I'm making a total mess of this problem, but anyway, plug it in there, you get 10 minus 1 is 9, the square root of 9 is 3, and 3 does not work in the g of x function. So I'm going to put a little comma here. X is greater than or equal to 1, comma, x not equal to 10. That's the way that we compute the second portion, or the second half of that restriction. That was the easy one. Now let's go to the harder one. The harder one is when we're trying to find f of g of x. So in this case, what I'm going to do is I'm going to grab these two guys here, and I'm going to move them down. I'm going to take this guy down here. I'm going to take this guy down here. And we're going to try to figure out f of g of x. Let me just extend the page here. All right. So f of g of x. That means we're going to start with g. So I'll put in another bucket here. This time we're going to start with g. So this will be our g, and this will be our f. Here's our real bucket again. And we see this time we're going to process through g, and that's because f of g of x is what we're looking at. We're going to do the g function first. We know that x cannot equal 3 here, so we're going to write that. And in our domain, we're going to actually start it out by saying x cannot equal the number 3. That's just realistic, because that's the first function we go through. This time, the f of x function, we know that in this function, the x value has to be greater than or equal to 1, but what we really need is g of x has to be greater than or equal to 1. Now this gets to be a little bit of a nasty problem, because 2x plus 1 over x minus 3 has to be greater than or equal to the number 1. But that's an inequality that we haven't seen in a while. In this case, you can't really work this unless you have a 0 on the right-hand side, so we're going to have to write this out as 2x plus 1 over x minus 3 minus 1 greater than or equal to 0. There's a little bit more work to be done in this problem. Slide this back up just a bit because we've got to bring this together as one fraction. 2x plus 1 over x minus 3 minus x minus 3 over x minus 3. Let me show you exactly what I'm doing with this one. I'm going to have now an LCD x minus 3. And if it's all right with you, I will distribute this carefully and add it into the 2x plus 1. So I end up with x, and I end up with plus 4. All right. I'm going to make a little sign chart here. See where my fraction is positive and negative. The numbers that would go in there, positive 3, negative 4. And we see that our fraction would be positive to the right of 3, negative for numbers between negative 4 and 3, and positive for all numbers less than negative 4. So we're looking for places where this particular fraction is greater than or equal to 0. So we're really looking for the areas to the far right and areas to the far left. So in this case now, the x values we're looking for, and it does say equals, so keep that in mind. Those are going to include this number negative 4 and include this number 3. Well, notice that our original domain was restricting 3, so I'm going to cross that off. But I am going to say now that I see that the final interval of numbers that makes this work are going to be numbers that are less than or equal to negative 4 or greater than positive 3 over here. So I'm going to rewrite my domain a little bit. I realize x cannot equal 3, so I'm going to leave that out, but I'm going to write it this way. X is less than or equal to negative 4, x is greater than 3. And that was a very tricky one because of that inequality that we had to solve in the second part. Okay, I'm going to finish this video with one more, and that is finding the domain for f of g of h of x. This is a triple, so this one's going to be very crazy, but it should be fun too. In this case, f of g of h means that we're going to go and process through h. That doesn't look too bad at all. Then we're going to process through g, and then we're going to process through f, because f is the one on the far left. So if this is the case, from the real bucket, all reals are okay for h because that is a linear function. This will be h of x. The g function, we see that h of x cannot equal the number 5. So we're going to start right there. Our domain, since h of x cannot equal 5, I'm actually going to set it equal to 5. 3x plus 4 equals 5, or 3x equals 1, x equals 1/3. That's my restriction, and that's the number that I cannot begin with, is a number 1/3. So I'm going to write x is not equal to 1/3. If 1/3 had been in this bucket way over here, it would have come over into the h of x bucket and answered as a 5, and that's not allowed in g. Now notice that this is the g of x bucket, but it's not really g of x, it's g of h of x. And so we know that in this case, the f of x function will not accept a negative 2, so we're going to write g of h of x is not equal to negative 2. How do we calculate that? We have to kind of backtrack two different buckets here. So let's see here. First of all, we want to find out, is there any way that the g of x bucket could produce, or the g of x function could produce the number negative 2? Let's give it a try. 2x minus 1 over x minus 5 equals negative 2. Let's see if we can actually get it to be equal to negative 2. 2x minus 1 equals negative 2. Excuse me. Let me just back that up just a little bit here, just so that it looks pretty. Negative 2 times x minus 5, or 2x minus 1 is equal to negative 2x plus 10. For x is 11, x equals 11/4. Okay, wow, what did we just find? We found the number that came from this one here, 11/4, and after we put 11/4 into the g function, it ended up as a negative 2. So this is not necessarily the culprit yet. The question is, how did the h function at the beginning produce an answer of 11/4? So I have one last computation here. I'm going to take h of x, which is 3x plus 4 I'm going to set it equal to that 11/4 and see what x value was produced there. That's going to be 4 times 3x plus 4. And then I'm going to have 12x plus 16 equals 11. I'm going to slide this down just a little more here. I'm going to end up with 12x equaling -5, or x is equal to -5/12. And there we found it, folks. That is the culprit right there. That is the number that we're looking for, that little rascal from the real bin, excuse me, I'm going to rewrite this with the not equal. So x is not equal to 1/3. X is not equal to -5/12. And those are the only two restrictions here. Those two restrictions came from the g and the f functions tracked all the way back to this real bucket. And so that's why these things are so tricky, because you've got to trace them all the way back to the beginning. I hope that helps to work out a couple of those problems on the worksheet. And I'll give you another video right after this one.